So what we're going to do today is we're going to talk about what ROS is and focus on today about how ROS communicates. All right. So hopefully that'll enlighten you on what's happening behind the scenes, so it'll be easier for you to make those communication, do that communication stuff on your own later on. It's really not difficult once you understand how and why it works. You will have some homework on this. It's not a lot of homework because you do have your midterms that you're still doing. But since we have we have a week off here, right? Because we're giving you your feedback. It'll be fun to do some ROS homework. And yes, you'll be using some of the TurtleBot stuff. All right, so what is ROS? Anyone, what is ROS? Well, first, what does it stand for? What does ROS stand for?
Robot Operating System.
Good. So it's Robot Operating System. It is not, and I repeat, it is not an operating system. It is an IPC. It's an interprocess communication framework. It also has, the framework also has a bunch of tools, so visualization tools. The plumbing is the IPC portion. And with these tools, it allows you to debug your system, right? And so these tools, it also has a lot of capabilities because of the standardized method that you communicate with different nodes. So what does that mean when I say standardized methods between communication? What do you have to draw up in order to communicate with another process?
A contract.
Perfect, a contract. And that is going to be a lot of why we use ROS and why we have to make sure that we define, hey, this is the contract we're going to abide to, and that way all these other things can talk. And so so people can add capabilities relatively easily. And there's this big ecosystem. So that means researchers, hobbyists, professionals use ROS and then also give back to the community as well. It is pronounced ROS, like from Friends, not ROS. If you say ROS at a job interview, you will not be hired because they know that you have no idea what you're talking about. It's just ROS. We're specifically going to be using ROS 1. That's because that is the biggest one right now. The last class of this term will be 100% optional. There'll be 0 tests on it, but it'll be on ROS 2. And I do highly recommend everyone just enjoying themselves, maybe even bring a beer with you. And we'll be going over ROS 2 framework. And that'll even be after our final on everything as well. All right. So for more about ROS, link right there. But again, ROS is a middleware or an IPC. It is not an operating system. It uses a distributed model to communicate. So it's uses a publisher-subscriber model, which has become very popular among roboticists. And everything runs over TCP. So that means you can do a lot. You can do multi-process controls, which is what I like to promote. And you can do run on multiple machines relatively easily. ROS 2 makes it a lot easier, but you can do it relatively easily. All right. So let's see what. So let's go say what we can do with ROS. We're going to play the 10-year video really quick, so you can just see a few things that are ROS enabled. And I'm going to turn off the audio because it gets really because it's really annoying. There's a bunch of robots that utilize ROS, and they use those standard messages. And we're going to talk about messages today, for those who don't know. But this has been around since about 2008. originally developed by a company called Willow Garage, which was an offshoot of Google, and is now run by the OSRF, or Open Source Robotics Foundation. Again, it's open source under the BSD license, which is one of the most lenient of all licenses out there. So that's one of the reasons why people in industry has picked it up. They have a ROS I, or ROS Industrial. There's regular old ROS. We're working on a ROS M, ROS Military, as well as other flavors of ROS. It's very important for you guys to know that ROS is not secure. It is not good for anything that needs high reliability. All right. When I say high reliability, I mean like cars, right? So something that you need to guarantee performance, ROS as is not the thing to do. And the reason for that is it has not been unit tested to the extent that is really needed by most things, such as medical or Department of Transportation. So just to let you know that that's out there. But the move to ROS 2 will help alleviate that. We're in one of these videos over here, but we're going to stop that and go back to the presentation. All right, but both these links, you can watch those on your free time if you like, are in the presentation. So, main goals of ROS. So ROS is supposed to be thin. So ROS is designed to be as lightweight as possible, so it doesn't add a lot of processing bogging down to your to your main processes. Because again, ROS relies on what's called a multi-process-based control architecture. And that is exactly what it sounds like. It means you have multiple processes that communicate with each other to do closed loop control. When we write packages that work with ROS, it's very important that we write our libraries to be ROS agnostic, so that it doesn't actually have to work with ROS, but only at the very final stage of communication is where you use the ROS functionality. That way we can port over to other things later on. So as we do everything with ROS, the main focus, sure, should be doing stuff in ROS, but you need to make sure that you continue to do all of your proper software engineering aspects, with SIP and Agile and your project backlogs and your iteration backlogs and your bug tracking and your proper branches and committing history and all that stuff. All right, so that's, again, is the main focus of this class. And now we're going to develop on little robots, fake robots, while utilizing good software engineering techniques. ROS is very easy to test on because it has a built-in unit test framework called ROS Test, and so it helps with you building your helps you test your code and your controllers a little bit. So we'll go over that a little bit later. And scaling in ROS is relatively good because it runs over a network natively. So you don't have to do much effort in order to get good network communication between multiple different agents or multiple different controllers. So why ROS? Well, robotics is hard, right? So we have a lot of components. That means we have IMUs, right? We have cameras, we have joints, right? We have other sensors that all have to talk to each other. And are we going to write all of the drivers for that ourselves?
No.
No, right? There's no one single organization, not even Google or Amazon or the US government, that can write all the stuff we need to be successful in robotics, right? We need to take all of the knowledge that we have so we can grab, hey, here are the drivers for this IMU. Here are the drivers for this vision system, so we can make this robot to have the functionality that we want, right? Because what gives robots right now its value? If that makes sense.
Yeah.
What adds value to the robot platform? That's the phrasing I wanted.
Open source.
No, that doesn't add value. Let's say, so I actually have a robot right here next to me. You're not allowed to see it, but she's sitting right here. Right now, she doesn't move all that much, but she can do some really cool stuff. Well, she's physically capable of doing some cool stuff, but she can't actually do it right now. So what is going to add what's going to add the value to this robot? What's going to add the value to the robot?
Software.
Exactly. The software will add the skills to this robot that's sitting right here, and that's going to add value. All right. And so by integrating all these components, like, sure, vision, all right, but that doesn't complete our task. Oh, some grasper thing. Oh, that doesn't quite complete our task, but you mix those together, now suddenly it's making you martinis. And and the robot is working at a bar. Well, that has now added value, right? And you don't want to develop the vision system, and you don't want to develop the grasping system, right? You want to develop the task. At least that's a lot of computer scientists' job. ROS also helps helps foster code reuse and collaboration. Because ROS is uses strongly typed messages. All right, that means that, and I'll say it many times in this lecture, between controllers, there is a contract. So when you communicate, you have to abide by, this is your inputs, this is your outputs, so that everyone knows what you're talking about. And that allows other people to know what you're doing, what you're inputting, what you're outputting, so that they can then reuse your controller with relatively little muss and fuss. Right? Because how many people have downloaded some library and wanted to use it, but it was too confusing, right? I think we've all been there, right? ROS helps alleviate that a bit. And it has good debugging and visualization tools. All right. So, important points to remember. Again, this is open source in the BSD license, which is very, wide open. But not all of the packages are BSD. So remember that when you're looking them up, they're not all BSD. It is not a real-time system. What does that mean, not a real-time system? What does real-time mean?
Something like the system that we use in space, like spacecrafts, those are real time, right?
That's not what it means. That's an example. But what does real time mean? Good example.
I mean, running at the same time as the robot.
Okay, that's part of it. So running in human time. Okay. Anyone else?
Okay, so not real time means like in simulation?
No, that would be simulation time.
Okay.
But so that answer was only partially correct. So guys, if there's any terminology that you guys don't know, please feel free to ask, even if it's as simple as real time. So what real time means is that you have a set sampling rate, and that you do not deviate out of a certain bounds of that sampling rate or that control rate. So just like with the Ackerman steering, right? So I said 100 hertz, and that needs to be guaranteed within, 1%-ish, right, or 0.9%. So that is going to be real time with that constraint. Okay. So ROS is not real time because there's no timing guarantees. Okay? Now you can make it real time if you can start guaranteeing certain things, but it is not inherently real time. Okay? It does not adhere to industrial safety regulation standards. All right? ROS-I helps that, ROS Industrial, but as is, it does not. And it is designed to work with Unix environments, and it supports Ubuntu Linux. ROS2 is a little bit different, and it supports Mac, Windows, Linux, and it uses a different message passing platform, which we'll talk about on our last lecture. I've become a relative fan of ROS2. All right, so do we have any questions about the basics? Otherwise, we're going to start talking about the core components. All right, we're good? All right, so let's talk about the core components. First, we have a master server. All right, so this master server sits around and listens for what we call nodes to talk to it and ask it for, hey, does anyone have this sort of message? So we have to have one master server running on our ROS system. So this is kind of like your negotiator. We have a parameter server, which is a different server than your master server, because your master server only holds information about who has what type of data and where they are. Your parameter server also saves parameters, so actually saves values. So you can think of it as global values for your entire robot, such as joint offset, 29.768237 degrees. Then you have our messaging infrastructure. So it's a publish subscribe system, which we'll talk about, and we're going to do examples of that today, where it uses services and actions, and these two we'll talk about at later classes. We'll be talking about publishing and subscribing today. All right. We have logging. We're able to log either an entire one channel or everything into what's called a bag file. So you can replay what happened on your robot, which is a really good debugging tool. So we have diagnostic frameworks built in. It's built with C++, so ROS CPP, and Python, so ROS Pi. There are other unofficial support stuff for it. I think Lisp is unofficially supported, as well as Java, but these are the two officially supported libraries for ROS. So as standard message types, we're going to be talking about message types today too, for things like pose and sensor data and stuff like that. As coordinate frame management. Oh, are people trying to get in? I'm sorry. Yes. Yeah, so this is just a reminder for those. I had to click admit a few times today. Try to log in with your UMD address. That way you can just get right in. I could not figure out how to let anyone in. I apologize. I tried and tried. All right, so then we have coordinate frame management. So just like with the vision project, right? So part of that requirement was that you have the location of that person in reference to the robot frame, not the camera. So it helps manage that as well. We use a robot description language called URDF, Universal Robot Definition Format, which is an XML-based language to describe a robot that we can use in simulation or for other things. Command line tools. So let's go ahead. I uploaded for you guys. Let's make sure that it's there. So in files, and then ROS cheat sheet. So I uploaded for you guys a good cheat sheet. Come on, load. that has a bunch of the ROS command line tools, and we're going to be talking about and using those today. So, just like a LaTeX cheat sheet, I usually like to have one of these printed out and just put on my wall in case I forget, right? So it gives you what the main one is and what it does, some of the parameters and how to actually use them. Again, that's in your file section as well. I uploaded a Linux cheat sheet if you guys were interested in that. In case you didn't see it, the Jacobian stuff from last week is up here. And I also plopped in the C++ 11 style sheet as well. All right. And so good visualizations. We'll go over RViz another day. That's for like a GUI, so a 3D GUI. We're going to look at RQT graph today so we can look at our structure of how we're communicating. So we'll be using that today. And it has a bunch of standard packages as well. So as I'm talking, maybe if you guys want to bring up your Linux computers so that when we do these examples, we can do them all together. All right. So first, let's talk.
What version are we using for ROS?
So all of you guys should have 1804 installed, and Melodic is the ROS version for 1804.
Okay, cool.
Right. So all of you guys should have Melodic installed. So it's kind of nice what ROS has done is they do have LTS versions, and they come out with the LTSs of Ubuntu. So the latest one starts with an N because they do theirs alphabetically. So this one was Melodic, then the next one for 20 starts with an N. Let's go see what that is.
Noetic.
What was it called?
Noetic.
Nomatic?
Noetic. Noetic, I guess. Yeah.
Noetic?
Yeah.
They are so weird with their names, I must say. It used to be all turtle based. Is Noetic a Noetic Ninjames?
It's again some tortoise species.
Oh, okay. Thank you. Yeah, so I don't know why they go after turtles all the time. It's either an homage to the turtle bot, which is a style of robot that was done back in the 60s. Let's see, original turtle bot. No, these are all, was that CMU? Was it? Or is it MIT? Let's see, first robot MIT. All this new stuff is coming up. All right, I'll try and find that for you over the break. I think I have it in another lecture of mine. But it's a smaller robot that has, that was called a turtle bot because of how it looked, but it was not differential drive. So I think it might be an homage to that, or they just really like turtles. So anyway, where were we? We were past. Okay, so let's go ahead and talk about now some of the conceptual overviews of ROS core. All right. So ROS core is an important thing, and this is that thing that runs is that main server that does all of the communication and communication negotiations. So it's kind of like your broker. All right. So your ROS masters is your master node, and that is going to be located if you have a default setup. Will be located at your local host and the port 11311. Yay, palindromes. Out of curiosity, guys, why is this number used? Why didn't they use 111?
I assume some of the ports are reserved.
Okay, very good. So ports below 100 are very much reserved. All right. I mean, obviously you can use them if you want to, but it's very standardized below port 100. In general, below port 5000, you should not use because it's been pretty full with pseudo standardized ports. All right. Like VPN, I think like OpenVPN's like 1164 and that type of stuff. So what they did was they are extra cautious. I usually do the extra cautious as well. You go above 10,000. What is the highest highest port number that you can use in an IPv4 setting?
Is it the end limit of integer?
Exactly. So it's 65,000 something.
Yeah.
So you have between 10,000 and 65,000. And so they picked this port here because they liked it. All right, but so ROS master, you can define where your ROS master sits by adjusting this line. And what do you call it? To start our ROS master, we just type ROS core. All right, so let me, I'm going to bring up for you where'd my pen go? Uh-oh. There it is. Okay. Let me escape this. And I'm going to bring up my fancy dancy old tablet when they still took pens, but is relatively useful now. And we're going to draw an outline of what is happening with ROS core so that you can understand what's going on. All right. Let's see. I was teaching electrical engineering earlier today. It was fun. They were doing step inputs. Yay! All right, so ROS core is a process. So when we're going to be doing our testing today, we're going to open up a terminal, and each terminal will be their own process. All right. What we and this right here at the moment is at address local host. What is localhost address? What's another word we can use for localhost? Or what's the address that we can use for localhost? Anyone? Maybe you recognize this. So if you ever see the joke that there is no place like 127.0.0.1. Have you ever seen a t-shirt with that on it?
Yeah.
Yeah. So there's no place like home, right? So that's your, that's your home address. It never routes out. It's only for your computer. It's kind of a weird address, right? Why is 127.0.0.1? What does that mean? Why did they pick that address? Does it look special?
Looks good on a t-shirt.
Well, but why this? Why not 126 or 128 or 150?
I don't know, but like, does it refer to some rule according to which like IP addresses are distributed?
Not quite.
Okay.
That's more than net masking. But they could have picked any one for the standard one, but they picked this one because it's easy. And the reason why it is easy is we're going to go convert this into binary. All right. So we're going to go backwards. What is 1 in binary? And these are all 8-bit numbers, by the way. So what's 1?
1.
Well, no, it's 0, 2, 3, 4, 5, 6, 7, 1. Okay? Because this is 8-bit binary. What's 0? 1, 2, 3, 4, 5, 6, 7, 8. Right? So that's all zeros. And then the next one's 1, 2, 3, 4, 5, 6, 7, 8. Now, what's 127? 1, 2, 3, 4, 5, 6, 7, 0. So that's why it's 127. It was relatively easy to remember. Make sense?
Okay.
Just a figure that's that one might interest you guys as to why we have certain numbers and where they come from. But anyway, our local host maps to our home address there. You could, if you have multiple network adapters, you can set that as the address of your network adapter. So let's say you're connected to your home network, and your home network is a 192.168.0.1 network, right? So it's 0.x, and your computer, your robot is 192.168.0.42. Then you would just have this addressed. You just put that there, and then you'd force your master to be on that socket. Okay? So let's go ahead, and we're going to put up our ROS core here again. Now we're going to have what's called a node. All right? So a node is a process. And so these is, you can think of them as binaries. So they're running, right? They're independent of ROS core. So you can kill the node whenever you want, and it's not going to affect ROS core. We're going to call this node A. And we're going to make another one called node B. Now, our goal is to have node A to talk to node B. But how is that going to happen? Well, both of them know, because of our environmental variables, where ROS core is. So node A makes a request for some topic to ROS core. ROS core then responds with some address / port. So that's this one right here. So then it's like, all right, now that's the address and port of this guy right here. And how did he know that? Because initially this guy said, hi, this is my topic. So it announced himself. So now node A talks over some address and port. And then node B responds with, no, let's talk over some different port, right? Because ROS core will always give a standard port to do the initial negotiation on, because otherwise the nodes won't know where to listen. But per normal TCP/IP, it'll respond with some random port within a certain range, that's not being used, so that they can then both talk over that one. So the nice thing is, we only talk to ROS core when we negotiate that first talking transaction. And now it's just talking between these two nodes. Does that make sense? We're going to do some examples of that. So if it doesn't make perfect sense, don't you worry. All right. Let's talk a little bit more about conceptual overview of how the file system structure works. All right. I'm going to keep this up because we'll probably use it in a bit. So the ROS ecosystem uses a file system structure that is stolen from Linux, which is good, right? Because it's semi-standardized. So if we go back to, not that one, close tabs. Oh, that's a cute little robot. All right, so if we go back to the cheat sheet, we have ROS LS, ROS CP, ROS CD. Oh, these are all very Unix-like, right? So they're doing that to keep things kind of standard. Now within, look back here, and and every controller itself will be a ROS controller, a ROS program is called a package. A collection of packages is called a meta package, and we'll talk about that a bit later. Every package in its home directory, in its personal home directory, is going to have a package.xml file, which has information about that package. And this is some metadata, including its name, version, description, license, dependencies, etc. It'll also include specific information about what messages it uses, what services it uses, and its launch file. We'll talk about launch files next week, I think next week, but not this week. But launch files are very important. All right. So let's go ahead and do some. So one useful command is ROS pack. ROS pack stands for ROS package. Let me go bring up a terminal. All right, so let's make this bigger for y'all. And I'm going to kill that. That's a ROS core running there. Can everyone see this terminal here? Big enough?
Yeah, I can see it.
Yep.
Great. All right. So we are on a Ubuntu system on this. So you name, so we're going to do LSB release. So 1804. So exactly what we should have. And we are, so the first big command that you should know is just how you start ROS core. And you just type in ROS core. And then you should see something nice like this. To stop it, you can Control-C it. ROS pack is nice because it allows you to, among other things, list the packages that are available. So ROS pack list. And here are all of the different packages available on my system, which is a lot because I did the desktop full install. And you can do it on yours. Obviously, you can take in standard ROS, standard Linux commands like find or grep. So everything with Turtlebot in it. So Turtle Sim and all that stuff will come right out. All right, so let's go ahead and go to what it, so we briefly talked about a node, but let's go ahead and talk about how we start a node, stop a node, etc. So nodes are the little processes, these guys, that are running. An example of which you could have a laser rangefinder node that gets data from, this one could be getting data from, some sensor. And that's connected over USB. That's supposed to be USB. Right, so that's a laser rangefinder. So node B gets the data from the sensor and then publishes it and sends it to node A over some topic, which I think I just called topic. Does that make sense? So let's go ahead and run some ROS, and let's go get some information about what is running. So this is another window. So in this one, we're gonna go ahead and run ROS core. So now ROS core is running, and let's do what do we call it? ROS node list. So let's see what nodes are running. So the only node is running is ROS out. Now that's always going to be running. So that's this guy right here. That's our main server. That's our negotiator. So let's go ahead and see some information about that. All right. So that's going to be ROS node info, and then now we do need these slashes, right? Because this means root. All right, so the root of the topic list, and we're going to see that they can get very long. All right, so now it has some information. So we have so what it publishes. So it publishes on ROS out arguments. What it subscribes to. So it subscribes to ROS out of an unknown type at the moment. That just means that nothing has been published to it. And then here are the two services. All right. So let's look at the ones that it publishes. Let me go bring up. So there we go. Not that one. Where's my other? Over here. All right. So let's say we want to then look at one of these, what is inside of this message. All right, because this is a specific type of message. This is a ROS graph message /log. To find that, we're going to go ROS CD, and then we can go into. Let's actually look at sensor messages. All right, sensor messages is a nice, easier one to look at, and I believe that that's probably on my next slide, and it is. So we're going to go look at an example of sensor message, which they have a few built-in ones. One of which is vector3, which consists of three types, which is all float 64s, so X, Y, and Z. So this is basically a structure. That is, defined as a vector3 that has a value of X, value of Y, and a value of Z. You can have a structure of structures, just like in C++, that is linear and angular. This is what's called a twist message, right? So you have your linear, your X, Y, Z position, then you have your roll, pitch, and yaw, or your rotation around your X, rotation around your Y, rotation around your Z. So let's go ahead and look at some of these sensor messages, all right? So we're going to ROS CD into sensor message, all right? So in here, we should have a message folder, and we do. And let's go ahead and look at our, let's see, what one might be fun. Let's look at our range message. Why not? So VI range. Oh, it's capital R. All right, so our range message has a few different types in it, right? So we have one of type header, We have a uint if it's an ultrasound, if it's an infrared. We have an unsigned int 8 of what type of radiation type, i.e. Sound, IR, etc. Note how we have beautiful, what do you call it, units. I love units. Oh, they're wonderful. Because, for instance, this is a range sensor. We have minimum range, maximum range, and it says that it's in meters. This makes a big difference, right? So this is part of that contract, so that you know what you're sending. So what type of data you're sending. So it's not just distance data, it's distance data, it's in meters, right? So you should always adhere to these contracts that are in these pre-built messages. You can always make your own, but why is it better to use the pre-built messages?
It's easier to integrate into other projects.
Good, it's easier to integrate. And what else? You help future-proof it. All right, so if you use these standard message types in a standard way, that means if someone else comes up with a better way to do this problem, it will be easier to integrate their solution with your system. All right, so make sure that when you make your messages, you do keep track of what units you're using and everything, and that's going to be very important for your midterm, right? So that's going to be both for the vision group as well as the steering group, because there are units that you're going to be dealing with. Now, I didn't define what units you should be using, I don't believe, but you should be using units and define what they are, okay? So ROS CD, that was really easy, right? So if we do, so ROS CD, that's in our environment. So we can tab complete and look, here's all of the different packages that I have installed on this system. All right. So let's go ahead, we'll go back one directory, and we're going to go look at what's inside of our package.xml for this sensor message. All right. So here, what it says is it gives a version and the name and a description, the normal stuff. Who's the maintainer, right? The link URL, but also importantly, it gives you its build dependencies. So these are other packages that it depends on in order for it to run. So in this case, it needs geometry message, right? It needs message generation, needs standard messages, geometry messages. That's for the run dependency, right? So these are things you have to have installed on your system in order for this to run, all right? All right. So let's look a little bit more into these message types, right? And so here's an example of a message definition. So let's go ahead and I'm going to kill this guy over here. Come on, see. There we go. So let's do ROS, MSG, show, and then here we have sensor. This is the one that we looked at before, and laser scan. All right, so this is going to show us what that message looks like. All right, so here we have our standard header. We have a timestamp. We have a frame ID. So this is going to be an incrementing, number typically. Then we have float 32 angle min, float 32 angle max, time increment, scan time, etc. These are strongly typed. Why are these strongly typed? Anyone? All right, what languages do we use for ROS?
Python and C++.
Good, we use Python and C++. Great. So, what is Python a strongly typed language?
C.
What was that?
C.
Okay, C++ is a strongly typed language and Python is not, right? So we have to go with the best type of typing, the most restrictive type of typing that we can, right? So it can support the other languages. Plus, we want to make sure that it's strongly typed because all of this communication goes over the network, all right? And, oh, there's something in the chat. Sorry, my bad. What happened?
Oh, I did not use my university
Oh.
email ID.
Yeah, you're not the only one. Don't worry about it. It was like
Okay.
6 people. Yeah. Sometimes I don't notice, and I don't want you to miss class. That's all. All right. But because we send a lot of this data over a network, we need to know exactly how big these guys are. So when we go from one type of system to the next, we are able to read, hey, this is supposed to be an unsigned int8 or a 64-bit float. So it takes up this memory here, and we don't get some buffer overflows or reading from the wrong portion of memory. All right, so has to be strongly typed. But that's good because then we have specific contracts that we have to adhere to, right? All right, so let's go ahead and continue with this conceptual overview of what a topic is, because I keep on mentioning, a topic, and I keep on saying a node, and that they have these messages, right? So these messages, again, are just structures, right? Just like a structure in C++ or C, just a collection of primitive data types in a specific order. So topics is a popular way to talk among multiple different controllers or multiple different processes. And the way it works is that we have our node A and our node B. And this guy says, I am on some topic, let's say robot/r/awesome. All right, so this is the topic that that node B is publishing at. Node A, it does that negotiation with the ROS core, and then it is able to it's called subscribe to this topic and read the data on that topic. All right. And we can also have node C can do the same thing. And we can also have node N can do the same thing. And none of them have to know about each other, right? Node A doesn't have to know about node C or N, and they all get that information. Now, it is important to, oh, go ahead.
Professor, so
Yes.
who has the data, node or the topic?
Who has the data?
Yeah.
All right, so the data is, let's say this is the data here. We're going to call that D. Node B has that data. It sends D here, here, and here via TCP IP.
Okay.
But it comes from here. Okay, so then it goes this way, right? Make sense?
Yeah.
Now, this is not a broadcast system. So, and I think there's ways around it, but if you have 1, 2, 3 nodes, I believe that you're going to have 3 times the bandwidth usage for the same for that same node publishing. But we're going to check that today because I don't know if they changed that in Melodic. They do version changes. So that is, so a topic, all it is a name, right? It's like a street address, like, hey, I want to listen to this, or I want to read this newspaper, right? And then the data is inside the newspaper, inside a specific format. Okay. So I know that might seem confusing, but we're going to go ahead and we're going to do an example of this. All right. So let's go ahead and, so this is the example that we're going to do. And we're going to open up a few terminals. So let me make you smaller now. I know I should use some nicer text editors, but terminal stuff, but I'm an old fogey. What can I say? I do stuff the hard way. All right, so we have 1, 2, and you're already here. Let's make you a little bit larger. For those for those who don't use Linux, reset just clears your terminal and clears some values in it as well. It's kind of useful. All right, so we're going to do a few things. All right, first we are going to start our ROS core, and that's going to be right here. And we're just going to let it sit there. It is a process. It has to be in that terminal in order to run. If you close the terminal, it's no longer running. Okay? So they are separate processes. Now, we're going to use some built-in functionality. And what we're going to do is we're going to publish to a topic via the built-in functionalities, which that one is going to be ROS topic. What do you call it? Let me see if I can move stuff out of the way for the moment. There we go. So ROS topic pub for publish, and then we're going to define a channel, right? So I have the example here called chatter. I'm going to call it chatter. So I'm going to call it robots are awesome, right? And then we're going to call it std msgs and string. So this is the type. So this is a standard type. So this will tab complete. All right. And then we're going to say yes, because robots are awesome. So our message is yes. And actually, we're going to put a heart there as well because we love our robots. And we're going to add one more thing because we want to have this continually published, and we're just going to add an R and a 5. So that means it's going to publish at 5 hertz, but let's actually do it at 1 hertz. So this will punch. No, we'll do it 5. Why not? So this means it'll publish at 5 times a second. All right. All right. So now she should be running. Great. So now what we're going to do is we're going to echo that. So we're going to read that on this terminal right here. So ROS topic echo. And then before we echo, let's go ahead and see our topic list now. So ROS topic list. And this is going to list all of our topics. So we have ROS out, as we expected when we looked at the information about our ROS core. ROS ARD, as we expected when we looked at this information. Now we have robots are awesome. Now let's go ahead and do ROS topic info and robots, ROB are awesome. As we told it to be, it is of string message type. sorry, standard message type and string. It is this is the node, because we never named our node. That's and it's publishing, and this is the port that it decided to live on. So that's what ROS core knows about. So let's go ahead and do ROS topic echo. So just like echo in Linux, this is echoing whatever is on that channel. So it's going to be root and then robots are awesome. And now we should be seeing yes, 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 because of course robots are awesome, right? We love that. So what's happening here is, is exactly that, right? So both, this guy and this guy say hi to ROS core. Terminal 2, this guy says, hey, I'm publishing robots are awesome. This one says, hey, give me robots are awesome. So it says, okay. And then, what do you call it? So then it does that negotiation and says, all right, now here's the information. So now it gets the information. So let's talk about a few useful tools within, we're going to leave those two running. So we're going to look at some useful tools. We can do ROS topic HZ, I believe, for rate. And that's going to give us the rate of the rate at which this is publishing at, approximately. Let's see. Rate at about 5 hertz. That's not bad considering I'm doing this over a network, right? So we can also check ROS topic bandwidth BW. All right, and then we're going to say robots are awesome. And this will continuously say, all right, this is the bandwidth that's being utilized by these two. Now, I'm going to go ahead and open up another terminal. What is your IP address? So, all right. So now we're going to do another. So right here, we're going to do another ROS topic echo. And then it's going to robots are awesome. So we have about 50 bytes per second is the average right now. So we're going to go ahead and add another subscriber to that. Oh, it looks like they did fix that. Good. So it is broadcasting to all of those, which is nice. So now you're not using extra bandwidth, even though multiple subscribers are going to it at the same time. Is that nice? All right, so we're going to, what do you call it? I'm going to leave that running for a moment, and let's go over to the next set of slides, because so I'll show you kind of what happens when we put all of this together. All right. So put it all together. So let's say we have our ROS master, and let's say we have a camera node, right? So this node reads the camera, so this could be over USB, right? So you consider this a driver for a camera, right? So this is how the camera works. So it could be USB, it could be FireWire, it could be one of those HDMI to USB converter things. Either way, this guy does its registration with the ROS master. So everyone knows that, hey, I'm publishing image data, and you know where to find me. Messages. All right. And so the image processing node says, all right, give me your image data. So it subscribes to this image data. Yay. And this is on the computer of the robot. So then it's able to do its image processing on board right here, and it's able to grab that data. Maybe on your laptop, you also want to display that image. So you also subscribe to this, and you go ahead and grab that data. Does that make sense? Does this structure confuse anybody?
No.
No, great. All right. So we went over slightly how the initial message passing looks, right? But next, I'm going to show you a graph of how that initial how the negotiation happens between the master and a specific node. All right. So here's our ROS master. And the Hokuyu is a laser rangefinder. It advertises to the master saying, hey, I have scan, right, of type foo on port 1234. All right. So basically it's saying, hey, if you want anything from scan, that you can find me at scan on this port, and it's of type foo. So now the master knows this. So it has that in its little black book. Great. So now viewer's like, hey, I'm in the mood for some scan. Can you give me some, can you tell me where to find some? It's like, okay, well, it's of type foo. Is that all right? And it's at this address. Like, sure. So it comes back. Like, great. Now I know where to find this at. So it then connects over here on port 1234. It's like, all right, that's good. Now the Hokuyu says, that's fine, but we need to be careful. So let's not talk on 1234 because other people might want to get to me then. Let's talk, I'll give you some foo on port 2345. So different port. So that says, all right, I got that. So then it negotiates, does that connection again. Say, all right, now we're connected on this port. And so then it's able to send its laser scan data back. All right, so now this goes back and forth. So this negotiation takes a little bit of time, right? And it takes a lot of back and forth. So it takes 1, 2, 3, 4, 5, 6 back and forths just to initiate the connection. All right, so it is a little heavy when it comes to networking as compared to other methods, but it does work. So let's go see this in action. All right. So right here, I'm going to kill this one, and I'm going to exit because I need to add X forward in. All right, so what I'm going to do now is I'm going to kill this, this, and this. All right. So this right up here was that publisher. All right, and this right here, and this one right here, I'll make these smaller. This was the subscriber 1, and this was subscriber 2. And that's just ROS core. And this right here is where we're going to play around with. And let's see if I can put the notes. Well, we'll just go on from the next are just some. We'll look at the graphs later. All right, so now what we're going to do is we're going to use, there's a set of tools called RQT. And at first, we're going to look at the RQT graph, which will show us how everything is connected. All right, so let's go ahead and let's type in RQT _ graph. So now it's going to give us the connection setup of our whole system. Oh, isn't this beautiful? I love this. Isn't it such an amazing, complex system? Why is it blank? Anyone?
There's nothing except ROS code. There's nothing going on.
Exactly, nothing going on. So let's go ahead and start publishing over here. All right, and then we're going to go ahead and refresh this guy. So now we have a topic, right? Nothing's happening, right? It's just a node, right? So this node right here, because no one's subscribing to it. All right, so let's go ahead and I'll make this. There we go. So now we're going to go ahead. I'm going to start one more node. One more reading. So now we're reading robots are awesome. I'm going to refresh this. There we go. And so now we see that robots are awesome, and this guy is so this guy is sending data to this guy. Let's see. Topics all. Okay, let's do just nodes only. All right. So, well, that's nice, but now let's go ahead and start this guy down here. Oh, go over here. There we go. So we're also going to echo down there. So let's go ahead and refresh. There we go. So now you can see he's sending data to both of these guys. This is a nice way to check out who's talking to who and on what topics they're talking on. All right. So having these visualizations like this are really useful. Right. So let's go ahead and keep these guys running. All right. And I'm going to cover that guy over. And now we're going to start a slightly different tutorial. And this is going to be, let's see, sh 192.168.0. Oh, that's not the address. 10.42.0.178. All right. So now let's go ahead, and all of you guys should have this installed if you did the ROS full install, ROS desktop full. We're going to do a ROS run, which will run one of your packages. And then the package name, this case is going to be ROS CPP tutorial. And we're going to run the talker. Okay, so all this is going to do is it's going to send out data called hello world, and it's going to increment a number, and it's going to publish it on a topic. All right. So let me open up a different window. Because remember, this is process-based, so I'm putting them all in different windows. So let's do. Now over here, we can go ahead and reset this, and we see that we have a talker node over there, right? But nothing subscribing to it. Let's do a ROS topic info, and I believe it's chatter is what it's publishing to. And so it is a standard message of string. Okay?
Professor,
What was that?
what was the command that you ran earlier for talker?
Oh, for talker? Yes, that is gonna, let me stop that. That is ROS run.
Okay.
So ROS run is how you'll start a package. There's multiple ways to start a package. We're going to start it this way at first. So ROS run, then the package name. So ROS CPP _ tutorials. And we're going to be running the talker of that.
Okay. I ran into an error of saying package not found, so we'll have to install this package.
Yes, you just probably did not install it. That's all.
Okay.
Yeah. So it's not a big deal if you didn't. If you want to make sure it's installed, just do, and you have enough space on your computer, do sudo apt install ROS melodic desktop, then full, and that'll just install everything. There might be melodic. Not T. There's no tutorials. You can look to see where that specific tutorial is from, but if you do the full, it'll install it for you.
Okay. I have
go ahead.
most of the other like turtle and like I've been working on ROS a little bit, so but I don't know. I didn't maybe I didn't install full. That's why maybe I don't
Well,
have.
let's go see where this guy's from, and let's go install it for you.
Okay.
Because if you have this question, other people might have this question as well, right? All right, so let's use the wonderful Googles. All right, viewing code. That's where she, okay. All right, let's see, ROS, ROS. So if you do ROS C, then ROS CPP, can you press tab and do you see anything like this?
No.
You don't get anything when you do ROS CD space and then you press tab?
Yeah, and like ROS CPP underscore co serialization trace tutorial. Yeah.
So you get core and you get
Yeah.
you get ROS CPP tutorials?
Right. Yeah.
All right, well, you should have then, because that's where it lives. So go ahead and ROS CD, then ROS CPP underscore tutorials. Okay, then press enter. So you should get this location here.
Yep.
Right? So it should be installed. So type ROS run,
Okay.
ROS CPP underscore TUT, and then that should tab complete.
It says usage ROS run package executable. ROS run will locate package and try to find, and if it finds, it will run it with outs.
All right, do you have a ROS core running?
Yeah.
Okay, you have ROS core running. In your terminal, in your bash RC, did you add this line?
Okay. Yeah. Now I get it.
Yeah. So what that line does is that line makes sure that all of your environmental variables are set, which includes your ROS master. Right. So it does not know where your ROS master is because it's not it was not set up.
Okay.
Okay.
Yeah. If we forget to add this line over here, then we'll have to do it manually each time when we open a new terminal, right?
Exactly. So just go ahead and add this to the bottom of your bash RC. Then you can just do source and then // or bash RC. Okay.
Mm-hmm.
Or you can run it manually each time. Running that source bash RC also allows you to switch between versions, which is useful and non-useful at the same time. All right. So where were we? Okay, let's go ahead and we're going to run Talker again. And over here, we see that Talker right there is sitting there, but no one's talking to it, right? So let's go ahead and do ROS run and then ROS CPP tutorial, and we're going to do listener. So now this one is just listening to this guy up here. So we can go ahead and refresh this and we say, hey, look, on the chatter channel, these two are talking, right? And so it's going from talker to listener. So just like these guys. Now, a beautiful thing about this is I'm going to kill our talker. So our listener is still listening, right? I'm going to start her up again, and she's still listening. Isn't that nice? So if you have, let's say your, let's say your camera fails. Oh no, my camera fails, so my process halts, right? The rest of your system didn't fail as well. That's one of the virtues of having a process-based architecture. Does that make sense?
Yeah.
So now listener's just sitting there and it's not listening to anything. But once she runs again, now she's listening again. And she's connected again. Now also, sure, I ran these two in the CPP tutorial. Ooh, look at that. Python. So now Python is also listening, right? So it's getting those same numbers. And if that stops, she stops. So seamlessly, we're able to talk between two different programming languages, right? Which is really useful. Why is it useful to talk between multiple programming languages?
Different sensors might use your different programming languages.
Good. Also, the controller that you might be trying to make, right? Because maybe if you're doing computer vision, you want to do it in Python, right? Because it's so much easier. But if you're making a closed loop controller for a, some rotorcraft, that might be in C, right? So as my grandma always said, use the right tool for the right job. And in this case, different programming languages have different strengths and different weaknesses. So that's one of the other nice things about ROS or using this type of IPC is that having it run over a network helps standardize things so that you can run different programming languages, which allows you to use the right tool for the right job. That makes sense?
Yeah.
Great. So let's bring up the let's do I have this stuff? I'm gonna kill this right over here. ROS topic BW slash. Oh, can I not do all? Damn it! I was hoping I could do all. Let's see, chatter. All right, so it looks like on chatter, it's about 200 something bytes per second for bandwidth. All right. So we talked about this guy right here. Let's go ahead and, so we just talked about, RQT graph. This is an example of a little bit more complex system, not much more. So you have, your joint state publisher publishes it to joint state, and that goes to different locations. You can follow, see who's publishing, who's subscribing, and on what channels, or on what topics, etc. Right? So it's just a little bit more complex version. So we did our publisher and subscriber walkthrough. So design benefits. So doing this process-based control is a lot like object-oriented programming, right? Because you can have multiple different instances of the same process running. They'll just be different nodes, right? So you make one joint controller, but you have 40 joints, so there's 40 separate processes, right? The topics are of strict typing, right? So it helps you standardize the the format. It helps you adhere to your contract. Contract. Very important. It's network enabled, which is nice. Not wonderfully network enabled. Again, ROS 2 does a lot better at it. So you can have multiple publishers and multiple subscribers. You can go both ways and multiple from multiple people. And what do you call it? It does have some what's called resource awareness, so you don't have to publish when no one else is subscribing to you. So it doesn't you won't be wasting bandwidth and sending data out into the nothingness when no one's listening. Which is a nice thing, right? If you're sending like camera data, that's definitely a great thing. Here are some resources that you can use on ROS, so feel free to look at them. Right here, you can look at using ROS with Eclipse. Here's a little tutorial on how to do that. One of the benefits of using a GUI is that you can have tab completion, and you can see all your functions that are available. So this will be a way of how to set up Eclipse with all of your ROS functionality on it. All right. So what we're going to do now is let's go ahead and let's clone examples. So you guys remember the examples address? So .git config. So remember, it's the Dan complex examples. So if you haven't cloned that, we're gonna go ahead and we're gonna go through a tutorial on how. Well, we're gonna make a publisher and subscriber. I'm gonna cheat a little bit and also make it go a little bit faster. And we're gonna do it in Python, but it's basically identical in C. All right. I more want to get you guys the concepts going of how this is all connected. Your homework, you're going to be making publishers and subscribers with tutorials as well. All right. All right. So go ahead and clone the example. So it's I'll just put that in the chat window. But you guys should all already have it anyway. All right. So let's go ahead into ROS. Now within ROS, we have a few different files, and we're going to make our own over here, just so we don't have to. We'll just use this window as a reference. All right. So this is the one where we'll be editing, and we'll be running them from this terminal and that terminal. All right. And let's go ahead and mkdir temp. And let's go into temp. All right, so let's go ahead. First, let's go ahead and make a talker. So we're going to first send information out into the world, all right? So let's go ahead and look at what's happening in Talker. So both in Python as well as in C++, you're going to make sure that you include your either ROS Pi, or in C++, you're going to include your ROS CPP. Here, what we're doing is we're creating what's called a talker. So that's going to be something that's going to publish on something. All right. So obviously we'll go to main, and then we're just going to try talker right here. So it's just this function. So the first thing that happens is we go ahead and, so let's go vi talk.py. Let's go ahead and grab those. Put those there. All right. So the first thing we do, is make a publisher. All right. So to do that, we're gonna make the object pub, and we're gonna be using ROS Pi publisher, and we're gonna be publishing on the channel chatter. All right, chatter, and then we're gonna define what type we are publishing on, all right? And that is of type string. Note how we imported type string. Now we could have just imported standard messages.msg, but why did we import from standard messages? Why did we import string specifically?
To save space, memory.
Oh yeah, to save memory, save space, but also you don't want to have all that other stuff clogging up your namespace, right? It'll help with your unit tests and make sure you don't get errors that you weren't expecting. So we're just being very explicit at what we're using. So we'll have string and then a queue size. We're going to set that equal to 10. So this is basically the publishing buffer. This is going to be the maximum size that it'll queue up before it flushes out into the network. Now, it depends on what rate you're going. It might flush at 1, or if you're going really fast, this will be the minimum size. This will be the maximum size it'll be before it flushes. Well, are you all familiar with what flushing means?
I'm not.
Got it. Okay. So what flushing means is you're queuing up pieces of data to be published somewhere. Flushing means that all of that data gets put out and gets sent. There's two times, there's two major times when things are flushed. One is when you reach the end of your buffer's limit. It usually automatically says, all right, it prints it out to the screen or it sends it over the network. Or I guess 3 times it would be. The second time would be at given time intervals. So there'll be timer interrupts that says, all right, print to the screen. All right, print to the screen. All right, print to the screen. Or send over the network. And the third time is when you explicitly say to send it. So you can think of it as, all right, we're putting messages in queue, and it won't go until we tell it to go. Okay?
Yeah, got it.
Same thing goes for serial. It's basically, it's a lot of how Linux works is with buffers and needing to be flushed. So here, again, we're just defining what node we're publishing on, and in reality, we should probably not say chatter. The reason why we're not going to say just chatter is because I want to do chatter from our home. I'm just going to be explicit about that right now because there are ways where you can make a publisher, which will then have itself namespaced with its own name. So it'll be /talk or /chatter or something to that effect. So we're just going to publish to the that channel right there. So then we're gonna make this node. So ROS pi dot dot init node. It'll be the same thing for or very similar for C++, and we're gonna name this node robot talker. All right, so that's just gonna be the name. And I actually don't know what anonymous is. I'd have to look that up. I do not remember. All right, and then now we're going to use a little neat feature for the moment. We're going to define a rate. Rate equals ROS pi dot rate 10, and that's going to be in hertz. So this is just defining how much you need to delay, using this function ROS pi rate. All right, and so this makes a little object right here that says, all right, this object will make sure that between each time this is called, it's about 10 hertz, which is a little bit different than just saying sleep for 0.1 milliseconds, because it's going to take into account everything that we've done down here. So we can then just say while true. I'm not going to, this is a more proper way to do it, but we'll just say while true. then we're going to say, we're going to define a buffer. And then we're going to say my, what do you call it, time is, and then we're just going to give it a specific time. So ROS pi dot get time. Now, so we could, right here is a ROS pi log info. That's going to print to the screen, but we're just going to use print. Yes, we're using Python too. And then we're going to do pub dot publish. And then we're just putting in our buffer. So that's just, we're just going to publish that. And then to make sure that we don't go ultra fast, we're just going to rate dot sleep, which is similar to time dot sleep. And then we put in like 0.1, similar to that. In fact, let's do it that way. Let's not do the rate thing. So now all this is going to do is it's going to publish the time at a rate of 10 Hertz. So let's go ahead and just do Python and then talker. Oh, and I screwed something up, of course, as I always do. Oh, still didn't do it. There we go. All right, so now it's just publishing. Yay! So we made a publisher. There's a few things. Let's just go over what we made again. Right. So here we made a publishing object on a specific channel or topic, very specific type, and we defined a queue size. We defined our node name. Then we made a buffer. And then we published on that buffer. All right. So now let's go ahead and look at how we're going to read that. All right. So now this is very similar. And so what we're going to do is, let's go ahead and quit that. All right. So let's also include our standard messages up here. And then we're going to just go to listener. And now within listener, we are going to initialize our system. So ROS pi.init node. So this makes our node name. So it's robot listener. And then all right. So then we're going to say what channel we are or topic we're subscribing to. So ROS pi dot subscriber. And we are going to subscribe to, I forgot what channel that is. So ROS topic list. We're going to subscribe to chatter. All right. And let's go ahead and see. I do remember with type string, but let's go look at it. So it's ROS topic info and chatter. So it is of type standard message string. All right. And now this next one is going to be the callback function. So whenever a new message is published, it's going to go to some function. So we're going to call it robot callback. So define robot callback. And the only thing that we're going to, and what is stored in there is data. So whatever's been published will be data. And then we're just going to print and then data dot data. Now you might see this little guy down here that says ROS pi spin. If we go through listener here, this is non-blocking. So if it just goes through here, it's going to exit. So all ROS pi spin does is it makes sure that we don't exit it. It'll just sit there. All right, the C++ version has a similar thing. All right, so let's go ahead and run that guy. So we say my time is, and it's listening to that guy. If we stop this guy, oh bugger, there we go. Then that guy stops, right? If that guy starts again, she continues on. Now that's good. So now let's go ahead and let's change something. Now let's go look at our talker, but vector 3. So right now we're publishing a string. And so this one's publishing a string and this one's listening for a string. Now it's going to be very similar, but now we're going to publish a type of vector 3. All right. So let's go ahead and change this to, whoopsie, wrong one, undo. So now here, we're going to go ahead and change this to, we're going to publish as a type of vector 3. And that's no longer our buffer. So we're going to say buff equals vector 3, so just a new instance of our buffer, and buff dot x equals I. So I equals 0.0. I plus equals 0.1. Right, and then we're going to go ahead and print buff and publish it. All right, so let's go ahead and see what happens. Now, mind you, this one's still listening for topic chatter. We didn't change that, but it's listening for a type string. Okay, what's happening over here?
Nothing.
Nothing, exactly. Why is nothing happening?
Because it's not printing a string.
Well, it's not that it's not printing. It's not publishing a string. Exactly. So the contract was broken. Right. So that's important. The contract was broken. So now it doesn't work. So let's go ahead and edit the listener. Which will be pretty, which is relatively simple, right? So we just, oopsie, undo. All right, so we add our vector 3, and then here we're just going to say vector 3, and then up here we're just going to print data.x. Okay. I'll just do right. And then here, Control C that, and then let's listen again. And now she's working. Isn't that nice? So do we have any questions on the different portions of our, on how to make or conceptually how to make a publisher and subscriber?
So did you have to make that robot callback function? You wouldn't be able to just print data.x in that subscriber node or in that subscriber line?
In here?
Yeah.
Okay, so that's a very good question. So this creates the subscriber. There is no data stored on the topics. Okay, so let me go bring up my. Let me do this a little bit graphically. All right, so let's go bring up this window again. I'll put it over here so you can see this at the same time. All right. And where did I put my tablet? There she is. All right. All right. So we have, let's say we have a time denoted by this. All right. So time goes this way. And let's say right here is we published some data 0. Okay. And if we then subscribe here, the next data, we will not get any data until here. So as 0, the system doesn't have any memory for what happened in the past. Okay. So what? So once, so our current time, we can only see forward. Okay. So that's why we use a callback function. Say, all right, when we get information, run this callback. Because otherwise, otherwise you're just not going to have any data, right? So it's how we have to do it is with the callback function saying, all right, we have new data on the line. Okay. Does that answer your question?
I think so.
What's your confusion?
So is callback a standard function? Or it's something that you just made up, right? And it just prints out.
The reason why I called it robot callback is because I want to make sure that you know it's just a random name.
Right.
But what this does is so it makes an interrupt. And this is the same thing in C++ and Python. So this makes an interrupt routine that says, I guess some of you guys don't program in microcontrollers. This is very common in microcontrollers. That's saying when an event happens. So that's saying when something else is published on this, that this is called. That's all it's saying.
Okay, and that has to be a function. It can't be a line of code.
That's correct. It's a function. Yep.
Okay, so you couldn't just put print data X in there.
Well, I'm pretty sure it has to be a function. I'm pretty darn sure.
Okay.
You can probably fake something. So what some people do is when this guy gets called, then they write to a global or protected or private variables so that other methods are able to read the most recent state data whenever they want to.
And so the robot callback in the subscriber doesn't have a input. Like it doesn't have a argument?
No, this does not.
The function does?
So the function, this right here, so this automatically assumes that it has one argument that goes into it, and that is the data that is published on the channel. and is of
Okay.
type vector3.
Gotcha.
And that's what this is
Okay.
right here. All right, so in C, it's good. You're going to say vector3 data, and then you publish the data. Does that make sense?
Yep.
Great. All right. Do we have any other questions about ROS and the concepts about how to make a publisher and subscriber? Oh, all right. So let's go ahead and let's go over what's going to be on the homework. And then if you guys have any other questions, we can go over that afterwards. Let's see, assignments. All right, so first of all, I'd recommend doing the reading first. Strongly recommend doing the reading first. The book is in the files section. So Intro to ROS. I believe I put that book. Did I not put it in here? Oh, A Gentle Introduction to ROS. There we go. So I put that in there for your convenience. So please read chapters 1 through 3, as well as there is a, just go through the introduction to ROS itself. It'll just explain to you the different, things that we're doing and the basic, aspects of ROS. Now, it's important to note that the most recent one is the one that starts with an N. We are on melodic. So they recently switched over because of 2004. Then, all right, so then for the programming assignment, remember all of our assignments, sure, I want you to, make sure that you do get the algorithm correct, but our main focus is on you doing the, the proper software engineering techniques, right? So making good branches, right? So doing your project backlogs and that type of stuff, all right? Okay? So make sure to follow that type of thing. Make sure you commit a lot, right? And make good and make good commit comments. So here are a few tutorials. I'd like you to go through. They go very quickly, so it's not overbearing on you. So do the C++ ones and instructions on what you should submit on GitHub. So you're just going to submit your GitHub repository link on Canvas. All right. Also, do not commit your entire. Let's go over the Catkin build space as well. Do not commit your whole Catkin workspace. Only commit your package, please. I don't want your dev directory and all that stuff in there. All right, one more thing is there is a ROSCon. So it's the ROS conference. It's a yearly conference that typically happens during ICRA or IROS. Here is a link to the 2018 ROSCon. So I went to that one. That's why I linked that one. They also have 2019 posted as well as the previous ones. Please pick a talk or two talks and write a one-page single-space overview of that talk. All right. There are a plethora of topics, so pick something that you like. There's everything from perception to manipulation to controls to security, all in there. This was in Madrid, and that was a pretty good one that year, I must say. So So we usually don't do big writing assignments, but please do, write that. All right, so do I have any questions? Okay, so now let's go ahead and talk about what do you call it? I mentioned ROS uses what's called Catkin as its build system. Did everyone set up their Catkin workspace yet?
Yeah.
Great. Okay, so hopefully everyone did. This is a new computer to ROS, so let me go make it now. So make dir p, and we're gonna do catkin workspace, and we're gonna make the src directory with that. And then we're gonna do our catkin make. And this is just gonna set up everything in our directory, including the dev folders and the executables. All of your projects go inside the src directory. The tutorials will be very clear about that. And I'm going to go ahead and source devel setup.bash just to get everything all set up for me. And then I'm just going to go ahead and look at my ROS package path just to make sure that it is correct, right? So that added my catkin workspace here into my ROS package path, right? So home, Lafaro, catkin workspace, src. So now it knows where to look, as well as opt, ROS, melodic, shared. All right. So only share what is in your src, right? When you do this, don't share after you build it, things go into your devel, don't share that. All right.